area method for factoring. I think they work great. They're just not my favorite or preferred method for doing it. I think one of the downsides with the X method is that you do have to find, especially when, or well, let me back up. When you're using the X method in the third term, the constant term is negative, you have to find the sign with it too. So if it was negative 42, we have 1 and negative 42. We have negative 1 and 42. We have the positive negative case all the way down. Does that make sense? But I also haven't done the X method in quite some time. So, not that I have anything against it. The main method I use is a little bit different. And if the way that I do it makes sense, use it. If the X method still makes more sense than the way I do it that way. Now, with every factoring method that I know of, I always start with greatest common factor. That's the main one we start with. Then I normally go with 3 sets of parentheses, 2 sets of parentheses with 3 spaces when we're dealing with quadratics. When we start dealing with higher degree polynomials, we have different methods we use. Then unlike the X method, I say we find the sign next, and I'll put that in here in a minute, because unfortunately, this one we don't have to do that with. Secant squared of theta minus 1, we want to factor it. We're not used to using tangent, secant, sine, cosine, cotangent, cosecant, dealing with factoring. We're used to X or Y. We're used to a single variable, yes? So we're going to use a special method to factor or to help us solve. And it's called U substitution. And incidentally, we use U for U substitution. And we pick U to be a certain expression. And in this case, I'm going to pick it to be secant. Secant of theta. I'm not going to do secant squared. I just want secant of theta. Because what this does is really this here, we'll write it out this time, is telling us really that we have secant squared minus 1. We're squaring our secant term. This is all this is telling us. Because in either one of these two forms here, it's kind of hard to see what secant squared minus 1 would factor to be. It's not something we're used to. So we're going to use U substitution. I'm going to say secant is going to be the same as U. And in this equation, everywhere there's a secant, I'm going to replace it with the letter U. So secant is now U squared minus 1. So I'm not even going to look at secant squared. I'm just looking at U squared minus 1. Let's factor it. This can sometimes be a little bit more easier to see how we factor it. U squared minus 1, well, that there is a difference of perfect squares, yes? We can see that is a difference of perfect squares a little bit easier than we can say secant squared of theta minus 1. They're both a difference of perfect squares. And just as a reminder, a squared minus b squared is the definition of a difference of perfect squares, and it factors to a plus b times a minus b, where a and b are our terms being squared. So in our original problem, we would have plus and minus. Our u squared, our a, the term that's going in place of a would just be u and Now we need our b term because we have 1, so we're really wondering what squared. Well, it's kind of an odd way to say it because what squared is 1. Let's just 1. So u squared minus 1 factored is u plus 1 times u minus 1. But we can't stop here because we used u as a tool to help us factor. But u is what? Secant of theta. So really what this is telling us is that secant of theta plus 1 times secant of theta minus 1 is the actual final answer for this here. We used u as a substitute to put it in place of our secant to get it into a form that we're more comfortable with and is easier to solve, and then solved it from there. Any questions on this here? Okay, we're going to look at the next one. For tangent squared of x plus tangent of x minus 3. All right. Now, again, just like the previous one, I mean, we could start here and work our way through it, but I think it might be a little bit easier to think of this not as tangent of x but as u. Because a single variable is probably a little bit more easier for us to grasp, get our head around, instead of thinking of it as 4 tangent of x squared of x plus tangent of x minus 3. Because if we replace tangent of x with u, well, here we have tangent squared of x. So it will become what? U squared. Because we said u is just tangent of x. So here we have tangent squared, which is going to become u squared. Plus, here we just have tangent of x, so it's just u minus 3. So in some ways, this makes it a little bit easier when we're trying to think of properties or our factors. Because we get this here. Now, no matter what way we factor from here, the first step is always going to be, is there a greatest common factor? Is there something that goes into every term? Because if there is, we factor it out. Well, there's not. So this is normally where the X method, I believe, and I kind of differ. Because since it is a quadratic, we're going to have 2 sets of parentheses with 3 spaces. I don't always put the 3 spaces, especially when I do these. The 3 spaces is just a way for us to make sure the parentheses are far enough apart that we're not just cramming everything in and we don't have enough space for everything. But the next step I look at after this is the sign. I want to find the sign. Because this helps us get rid of trying to find the factors of -3. We don't have to say that -3's factors is -1 and 3, 1 and -3. We don't have to list them all out. Luckily for this here, there's only 2 if we consider the sign. But I think this is a little bit easier. Because when I look at for the sign, when I try to find the sign, I look at the third term. If the third term is positive, the signs are the same and they match the sign of the middle term. If the third term is negative, the signs are opposite. And I'm going to draw some stuff over the top. You don't need to draw this because it's going to get really messy really quick. The third term comes from this multiplication here. Well, if, let's say both the signs were plus. Well, a positive times a positive is a positive. That's something we've learned since before middle school. A negative times a negative is a positive. So if the third term is positive, the only way it can happen is if the signs are the same. That's the only way it works. That's why I think the first part of this is kind of nice, because third term, if it's positive, the signs are the same. Now, the match the middle term part, if you're not used to this or spent any amount of time thinking through this, which y'all haven't, there's no need to, we get the middle term from this here, the first times the last, and the middle two. In most all the ones we work with, I try to keep the first term, the factors of our u squared term, positive. If it's negative, I factor the negative out to make it positive. Well, with this here, I'm going to call it AB, AB. Our a times negative b would be negative AB. Negative b times a is negative AB. And we get this here. Okay. They're both negative, so the middle term would be negative. Our last term would still be positive, yes? If the signs are the same. So if third term's positive, the signs are the same and match the sign of the middle term, because we combine that middle term. It keeps the sign of what it is. Because if these had both been positive, means both of these would be positive, and that's positive. That's why I think this is nice. Almost there we go. Now, the other part of it, because that takes care of it, the third term is positive. Now, if the third term is negative, the signs are opposite. Is the only way we can multiply two numbers together and get a negative if one's positive and one's negative. That's the only way it works. So since the 3 here is negative, our signs would be opposite. One's positive, one's negative. You all right? A lot of information for first thing in the morning. And really, I'm giving you all of this not so much as you have to know this. I'm giving you this so that this step, which is very new to you because you haven't done this, I want to give you the backing behind it, why this works so nicely. And this isn't something I came up with. I was actually taught this. Now, the fourth step, which I haven't written up here yet, this does kind of fall along with the cross method, is to find the factors of the first and third term. Then plug in. And the last step is to check, just to make sure they work. Now, looking at the factors of the first and third term, the first term is 4u squared, yes? Now, most teachers, and this is not incorrect, it's not anything about it, we would look at all of them. So we would say 4u squared. So we have 1u times 4u. We also have 2u times 2u. And we would list all these out. And I think you're used to seeing that, yes? In every single factor, and both of those factors, what is in common on both sides of each factor? They both have something. They both have u, because the only way to get u squared, or x squared, or y squared is to have x and x, u and u, y and y. They're both going to have it, yes? So this is just my personal feeling. Since I know it's u squared, the only way to get it is u times u. I put it in there. And when I look at the factors of 4, I don't even bring u into account because it has to be there. There's only one setup. There's only one way it works. So why even worry about it? Let's just go on and plug it in. If there's only one set of factors, there's only one way it works. We're just going to plug it in. And the biggest reason I say that is because step number 5, this is one of the downsides to it. We just check it. We check it at the end. So we have this here. Well, the only factors of 3 are 1 and 3. Be nice if I had my marker back. I'm just going to plug it in. One set, plug it in. We'll check it in a minute. Now, we do need to pick the factors of 4 because there are 2 of them. Do we want to use 1 and 4 or 2 and 2? 2 and 2. And the last thing we need to do is check. And I have a feeling, even with the X method, they had you check it, multiply back out. And if I'm assuming right, I do want to get this yellow. The first thing we did was 2u times 2u, yes? There's a reason I did it in a different color. Where did we get 2u and 2u from? 4u squared, yes? They're the factors of it. So theoretically, shouldn't they always multiply back to be 4u squared? Why check it? Because that's where they came from, so they should go back there. 1 times negative 3 is, so the factors of it, that's where we got it. The only way either one of these would not match up is if we factored it wrong. But the one that always changes, depending on the setup, is the middle term. That's the one that changes. That's the one we need to check. So normally when I factor, I don't check either one of these 2. The ones I check are these 2. Because these are the ones that are actually changing based off the setup. 2u times negative 3 is negative 6u. 1 times 2u is plus 2u, which gives us, is that the middle term we wanted? No. Okay, so we can switch the 1 and 3, but that's not really going to do anything because we still have 2 and 2. All it will do is change it from negative 4u to positive. So we can switch the numbers in front of u to 4 and 1. We don't necessarily have to write the 1 because it's understood. Now we can check this here. U times negative 3 is negative 3u. 1 times 4u is plus 4u, which gives us a positive u. Is that what we wanted? So that is the correct factors. But we're not quite done. Because what did we say u was taking the place of? Tangent. So what we have is tangent of x plus 1 times 4 tangent of x minus 3 are our 2 sets of factors. Questions on this here? Now again, as I said at the beginning, and I will stand by this every single time, if this way of factoring is not something you like or something you understand well and you want to stick with the other one, do that. All right? I'm not going to count it any different than if you did it my way or the other. Because it's more about you understanding than it is about you learning a specific way to do it. But if this way does make sense, use it. If it doesn't, don't. We ready for the next one? And they throw us a curveball. Because, let's look at the equation. Cosecant squared of x minus cotangent of x minus 3. Those are not like terms. Even if we did use substitution for cosecant, well, it's not going to replace cotangent. And if we do it for cotangent, it's not going to replace cosecant. But anytime you see a square, there's one set of properties we're going to always go back to. Pythagorean. Because 1 plus cotangent is squared is equal to cosecant squared. So what that's telling us is that this right here can be replaced with 1 plus cotangent squared of x You're good. You don't have to stick around for this here. Questions about how we rewrote this? If there had been a negative sign in front of the cosecant squared, we'd had to apply it through the rest of this function here. For the 1 plus cotangent squared would have become negative 1 minus cotangent squared, or vice versa. Now we do need to combine like terms. Our 1 minus 3 is going to become negative 2. I'm going to use u substitution again. So what we're saying is that I have u squared minus u minus 2. Is there a greatest common factor between u squared u and 2? Well, no. So I'm going to do 2 sets of parentheses, just to kind of give us the space that we need to factor this. And the next thing we do is I'm going to look at the third term. If the third term was positive, the signs are the same and they match the sign of the middle term. If the third term is negative, our signs are opposite. Here it's negative, so we have plus and minus. Factors of the first and third term. Well, our only factors of u squared are and u. So we can go on and just plug those in. Factors of 2 are 1 and 2. Which one would be positive? Which one's negative? Right. Now, the middle term in this case is negative. So most likely we want the bigger term to be negative or the bigger product to be negative based off of the numbers in front of u. And lastly, what we can do is check to make sure this does work. U times negative 2 is negative 2u. 1 times u is plus u, which does indeed give us negative u. So this is the correct factoring setup. But to finish this out, we have to replace u with cotangent of x plus 1 times cotangent of x minus 2. And that's our final answer. Questions on this here? We're ready for the next one. Secant squared of x plus 3 tangent of x plus 1. Well, if we did go back and look at the Pythagorean identities, 1 plus tangent squared is secant squared, yes? So we can replace it. These squares are very helpful. Those Pythagorean identities are very helpful, especially with solving, because we'll get to solving in the next section. But they are very helpful with this here. And if we don't have them, we can sometimes use a scalar multiply through by a sine, cosine, tangent, secant, cosecant, cotangent to get that square, to get what we want. Now here we're saying tangent squared of x plus 3 tangent of x plus 2. Assuming we want to use u substitution again, it does make these a little bit nicer. And we're going to call it tangent of x. And what that'll tell us is that we have u squared plus 3u plus 2. Our signs, well, since our third term is positive, the signs are the same and match the sign of the middle term, which is also plus. So we have plus and plus. Incidentally, we still have u squared, and its only factors are u and u. Factors of 2 are 1 and 2. And especially with them both being plus, this is the only way we can set it up. So if it doesn't work, it means the original one wasn't factorable to begin with. Well, u times 2 is 2u. 1 times u is plus u, which does indeed give us 3u. So this is the correct way to factor it. The last thing we need to do is plug in tangent of x. So we have tangent of x plus 1 times tangent of x plus 2. And that's it. Questions on this here? Rewrite the following expression in non-factorial or fractional form. We need to get it out of a fraction. Now, what we're going to do is rationalize the denominator. That's really what we're going to try to do. And there's a reason to it, and it will make sense as we do this. It's not something that most would instinctually go towards. Multiplying the top and bottom by 1 minus sine of x. And there's a reasoning behind it. And the reasoning is revolving around our sine squared of x plus cosine squared of x is equal to 1. Because if we solve this for cosine, we got cosine by itself. It will tell us that cosine squared of x is equal to 1 minus sine squared of x. So if I can rewrite the denominator as 1 minus sine squared of x, I can have it as cosine squared. And we can easily change cosine to something else, because our cosine of x is equal to 1 over secant of x. Or incidentally, secant of x is equal to 1 over cosine. So if I can get the denominator just in terms of cosine or just in terms of sine, tangent, or cotangent, one term where I don't have this addition or subtraction, then I could rewrite it as its reciprocal. And it seems kind of odd the way that it works with this here. Why is this going to work? Well, the numerator 1 times 1 minus sine of x is just 1 minus sine of x. This is multiplication of 1. Now the denominator, we have to actually distribute this out. Well, we're in green, we're going to stick with green. 1 times 1 is 1 times negative sine of x is negative sine of x. Sine of x times 1 is plus sine of x. And lastly, sine of x times negative sine of x is negative sine squared of x. Apparently we're going to scroll. The numerator is still 1 minus sine of x. The denominator, well, middle terms cancel, giving us 1 minus sine squared of x. As we just said a minute ago, 1 minus sine squared of x is the same as cosine squared of x. Now this last part is a little bit of manipulation with this, because really we're saying that we have 1 cosine squared of x is being multiplied by 1 minus sine of x. I write it this way so it's a little bit easier to see what we're about to do. Because 1 over cosine of x is the same as secant of x. So 1 over cosine squared of x is the same as secant squared of x. Do we have fractions anymore? No. So that's one of the final answers. The other way we could write it is secant squared of x minus secant squared of x sine of x. I would stick with that way there because that other way is not any simpler. It's just we multiplied it out. Questions on this here? It is funny. It is very different than everything we've used up to this point. The only thing this connects closely to is our rationalizing the denominator with complex or irrational terms. Questions on this here? Rewrite the following non-fractional or expression in non-fractional form. So we have cosine squared over 1 minus sine squared. We're going to do a similar thing as we did on the last one, but we do have to change one small part. We're not going to multiply the top and bottom of this by 1 minus sine of x. We have to multiply it by what? 1 plus. Because the denominator already has the minus, we need the plus. Is really what we're using is the difference of perfect squares. Now the numerator, I'm going to leave it in this form. Leave it in this form here, and we'll go from there. Because I see there's actually another way we could have done this, but that's fine. The denominator will have to distribute again. 1 times 1 gives us 1. 1 times sine of x is going to be plus sine of x. Negative sine of x times 1 is negative sine of x. And negative sine of x times sine of x is negative sine squared of x. And just like the last one, these cancel, leaving us with cosine squared of x times 1 plus sine of x all over 1 minus sine squared of x. And just like the last one, one minus sine of x is the same as cosine squared of x, yes? Oh, wait a minute. What do we have on top and bottom now? That's it. Questions on this here? Now I did say once we started this that there was another way to do this. And there is. Because using what we used on the last one and this one, cosine squared of x is the same as 1 minus sine squared of x. Now for this one here, how I'm showing you, I'm not going to use u substitution. I'm going to use the fact that this is a difference of perfect squares. So 1 minus sine squared of x would be 1 minus sine of x times 1 plus sine of x over 1 minus sine of x. Well, these cancel, leaving us with 1 plus same place, different method. This one, especially if you're able to factor the 1 minus sine squared easily, it's a little bit quicker. U substitution would have taken another step or two, but we would have gotten to the same place. Questions on this here? Okay. We'll save the last 5 for tomorrow.